Dear students, all are welcome to my 5th class on atomic structure. In my last class, I discussed the dual behavior of matter. That is a de Broglie's equation. Lambda is equal to H into MV or H by P. Here lambda is a wave character, MV is a particle character. So, for the macroscopic particles, this lambda is so small because m is considerable high, though they are considered as only the particles. But a microscopic particles like electron, proton, molecules, atoms, this m is very small. They have a considerable lambda. Therefore, these particles have both the wave character and particle character. Okay, this is the one thing. This is called the de Broglie matter and wave equation. So the second one is uncertainty principle. Here, delta x into delta v equal or greater than h by a 4 pi m. Here, what it says, it is impossible to determine simultaneously the accurate position and accurate momentum or velocity of an electron. So here he has given the mathematical equation here, delta x and delta v equal or greater than h by 4 pi. What is delta x? It's a error in measurement of position. What is delta v? Error in measurement of velocity. So minimum error is what? H by 4 pi m. So this uncertainty principle is applicable to only the microscopic particle. Suppose if you want to determine the exact position and exact momentum of your electron, this uncertainty, this two product will considerable. Yesterday I shown that by using a calculation. But for macroscopic particle, for example, the moving of ball or moving of bullet, for these particles, they have the very small delta x and delta v. What does that means? They have their position and their momentum or a velocity can be measured certainly. So here the Newton's law works. After that, this means the smaller particles like electron or atoms or molecule, they have a dual behavior. Second thing is their velocity and their momentum cannot be determined simultaneously. So after that, I discussed why the Bohr's theory has failed. The reason for the Bohr has considered the electron as a only particle. He given the definite path for the movement of electron. But these two theories totally against the Bohr's view of orbit. So the Bohr's theory has ruled out. After that, the quantum mechanics. What is a quantum mechanics? It's a theoretical science which deals with the motion of microscopic particles like electron. They have a considerable wave and particle properties. So after that, the Schrödinger and Heisenberg independently developed this quantum mechanics. The Schrödinger has given the wave function equation. So this Schrödinger equation is solved for hydrogen atom. What is that? The solution shows the presence of various energy level and their wave function. So these are the various energy levels and their wave function are characterized by 3 quantum numbers. So that thing we have discussed in my last class. After that, finally, I started this one, atomic orbitals and quantum numbers. So what are atomic orbitals? What are atomic orbitals? This is just a wave function. So here around the nucleus there are various atomic orbitals. and they have a corresponding wave function also. So, this atomic orbitals, how they are differ? They are differ by, one is a size and energy, another is a shape, the fourth difference is the orientation. All these atomic orbitals are characterized by three quantum numbers. The first is the principal quantum number. The first one is a principal quantum number n. So, yesterday I discussed this thing. What is the principal quantum number? What are the values of principal quantum number? 1, 2, 3, 4, so on, positive integer. It has a values, positive integers. See what it actually describes? Size and energy of the orbital. What is the principal quantum number described? A size and energy of the orbitals. So, here this principal quantum number also called a shells. So, these shells are also designated by letters K, L, M, N, so on. So, if n is equal to 1, that is a K shell, n is equal to 2, L shell, so on. So, after that, the maximum number of orbitals in each shell is n square. Suppose the first shell, let us say n is equal to 1 K shell, how many orbitals are there? N square means only one orbital is there. So, in a second shell, the L shell, how many orbitals are there? 4, 2 square. In M shell, 3 square, 9 orbitals. In N square, the 16 orbitals are there. If number of the principal size of the principal quantum number is increases, the number of orbitals is increases. So, these things I discussed in my last class. The second one is the azimuthal. Azimuthal, a quantum number. See, it is designated by L, a small l. So, what is azimuthal quantum number described? A shape of the orbital. Shape of the orbital. So, already I told these orbitals are they have a different shape and energy. The first to describe the shape and energy. The second one is describes the first principal quantum number describes the size and energy, and the azimuthal quantum number describes the shape of the orbital. So, next, what are the values of L? The for given value of n, L can have the value L is equal to 0, 1, 2, so on, n minus 1. So, these are called as subshells. These subshells are present in each main shell. So, see, suppose n is equal to 1, n is equal to 1, n is equal to 1, that is a K shell. So, what is the value of L? L is equal to 0, that is only one subshell is present in a K shell. So, similarly, suppose n is equal to 2, L is equal to 0 and 1. This 0 is present in a first shell also, in second main shell also. So, if n is equal to 3, L is equal to 0, 1, 2. If n is equal to 4, L is equal to 0, 1, 2, 3. So, these are the possible values of L for given value of n. The values of n, L depends upon the values of n. Okay. So, here these are designated by subshells are designated by letter S, P, D, F, like that, G. These subshells are designated by letters S, P, D, F. If L is equal to 0, that's a S subshell. So you look that L is equal to 0 is present in a first shell also. L is equal to 0 is present in a second, third, fourth, like that. So that means this S subshell is present in all the main shell. How they are differ? They are differ by a size. The first quantum number explains the size. So that means here is L is equal to 0. Here also you have L is equal to 0. That means this is also S subshell. This is also F subshell. How they are differ? They are differ by size. This principal quantum number describes the size. So, but they have the L is equal to 0 means both have the L is equal to 0 means both have the same shape. ಈ azimuthal quantum number ಯಾವುದರ ಬಗ್ಗೆ ಹೇಳ್ತದೆ? shape ಬಗ್ಗೆ ಹೇಳುತ್ತೆ. If azimuthal quantum number is same means the orbitals have azimuthal quantum number same means they have the same shape. Okay, so the L is equal to 0 means S subshell. L is equal to 1, it's a P subshell. L is equal to 2, it's a D subshell. L is equal to 3, it's a F subshell. L is equal to 4, it's a G subshell. So these are the subshell. The shape of the orbital is present on the which subshell it belongs to. L is equal to 0, L is equal to 1, L is equal to 2, like that. See, after that, these things I discussed in my last class only. See, after that, the third quantum number is a magnetic quantum number. So it is designated by M with a subscript L, ML. It's a magnetic quantum number, ML. So here, see what it describes. It describes the orientation. It describes the orientation of the atomic orbitals. So here, what are the values of ML? The values of ML is depends upon the values of L. For the what are the ML values? The values of ML is equal to minus L to up to 0 up to plus L. All the integers from negative L to a positive L. See, what are the values of M? All the integers from negative L to positive L. For example, if L is equal to 0, ML has only one value, that is a 0. So that means L is equal to 0 means that is a S subshell. M is equal to 0 means it has only one orientation. So then L is equal to 1, it's a P subshell. M is equal to, sorry, L is equal to 1. ML is equal to minus 1, 0, plus 1. For L is equal to 1, M has how many values? Minus 1, 0, plus 1. It has a 3 orientation. The L is equal to 1 means what? P subshell. P subshell has how many orientation? 3 orientation. See, so L is equal to 2. L is equal to 2, ML is equal to minus 2, minus 1, 0, plus 1, plus 2. How many orientation? 5 orientation. L is equal to 2 means what? D subshell. The D subshell has a 5 orientation. So this minus 2, minus 1 only the designation. See, no need to worry, it's the minus and plus. So this is the magnetic quantum number. Magnetic quantum number explains the orientation of the atomic orbital. In the L is equal to 0 means S subshell, it has only one orientation. So L is equal to 1, it is a P subshell, it has a 3 orientation. and L is equal to 2, it is a D subshell, it has a pi orientation. L is equal to 3, that is F subshell, that has a 7 orientation. Okay. After that, now I think it's the 3 quantum numbers. One first quantum number, principal quantum number, explains the shape, size and energy. The principal quantum number explains the size and energy. The azimuthal quantum number, this azimuthal quantum number defines the subshell in which the electron is present. Here, how many orbitals are possible in each azimuthal quantum number? The 2l plus 1 orbital. How many orbitals are present in each subshell? 2l plus 1. Suppose L is equal to 0, that is a S subshell. How many orbital is present? Only 1. If L is equal to 1, that is a P subshell. How many orbitals are present? 1, 2, 3. 1, 2 into 1 plus 1, 3. For the L is equal to 2, that is a D subshell. How many orbitals are present? 1, 2, 3, 4, 5. That is a home. In each subshell, how many orbitals are present? 2l plus 1. Each main shell, how many orbitals are present? N square. So, after that, see, now you can look the values. You can look the values of all 3 quantum numbers. I can write here. The N, L, M, Mn. Suppose N is equal to 1, N is equal to 1, L is equal to 0, M is equal to 0. K shell, L is equal to 1 means it is a K shell. How many subshells are present? Only one, that is a S subshell. You are writing the 1S because N is equal to 1. So, here M is equal to 0, it has a only one orientation. See, after that, N is equal to 2, L has a 2 values, 0 and 1. So, here 0 means it has a M as a 0, 1 means it is a 3 orientation, -1, 0, a plus 1. It's a, this is a S subshell, it is a P. L is equal to 1 means it is a P subshell. How many orientation? 3. If N is equal to 3, L has how many values? 0, 1, 2. L is equal to 0 means what? L is equal to 0, here the M is equal to 0. L is equal to 1, M has a 3 values, -1, 0, a plus 1. See, L is equal to 2, M is equal to -2, -1, 0, plus 1, a plus 2. How many orientation? 5 orientation. So, you look now, if N is equal to 2, how many orbitals are present? N square. N is equal to 1, the number of orbitals is 1. N is equal to 2, how many orbitals are there? The 4 orbitals. Out of that, 3 p orbitals and 1 s orbital. And N is equal to 3, how many orbitals are present? 9. 1, 2, 3, 4 and 5. It is a 9. Out of that, 1 is a s orbital, another 3 is a p orbitals and the d orbital, 5 d orbitals. The d orbitals have how many orientation? The 5 orientation. So, these are the what actually defines? It defines the size and energy. This defines the shape for multi-electron it some extent it defines the energy also. This is the orientation. Orientation of atomic orbitals. So that means the orbitals, suppose you write any orbitals, it is tagged with these three quantum number. Yavade atomic orbital number bekandre, it is tagged with these three quantum number. For example, I write the 2px. 2px. See, this 2 is a principal quantum number. It is belonging to a second principal quantum number here. And P belongs, the P, it's a azimuthal quantum number. It's L. X represents a magnetic quantum number. It's oriented along the x-axis. So, one is the principal, the number is a principal, defines the principal quantum number. The letter S, P, D, F, it defines the azimuthal quantum number. So, depending upon that, you can know the shape of the orbital. And one more is the X. The X represents the magnetic quantum number. For S orbital, we are writing 3s like this. Here, the magnetic quantum number for S orbital is only one orientation. Therefore, the magnetic S orbitals are not tagged with a magnetic quantum number. Okay. See what this means? The 3 is a principal quantum number, S is the azimuthal quantum number. So it's the 2s. Suppose I write the 2s. See what they are same. The S is same means what is the S represent? Shape. This shape is same. This number is different. This number is different means what they were different? Their size and energy wise they are different. Okay. So suppose I write the 3d x square minus y square. What is this one? 3d x square. Here 3 is the principal quantum number, d is the azimuthal quantum number, x square minus y square is the magnetic quantum number. Therefore, each orbitals are tagged with these three quantum number. These three quantum number clearly defines what is its size and what is its energy and what is its shape and which direction it is oriented. All this information the orbital provides. Okay. After that, these three orbitals are sufficient to define to describe all the electron? Then no, because each orbitals can accommodate a maximum 2 electron. Suppose I write the 2px. How many electron it can accommodate? The 2 electron can accommodate. So you are differentiated all the things, but you are not differentiated these 2 electrons. For that we need one more quantum number. So the experiment also shows, for example, in the discussion of the failure of Bohr's theory, the first limitation I discussed was the Bohr's theory fails to explain the finer detail of the hydrogen spectrum. Each spectral line has a doublet structure, or if you study the multi-electron atoms, each spectral line is when you look the spectral line with a high resolving spectroscope, each spectral line has a 2-3 closely spaced lines. These are called a doublet, triplet like that. This cannot be explained by these 3 quantum number. ಈ 3 ಕ್ವಾಂಟಮ್ ನಂಬರ್ನಿಂದ ಅದು ಯಾಕೆ ಡಬ್ಲೆಟ್ ಯಾಕೆ ಫಾರ್ಮೇಷನ್ ಆಗ್ತದೆ, ಟ್ರಿಪ್ಲೆಟ್ ಯಾಕೆ ಇರ್ತದೆ ಅಂತ ಹೇಳಲಿಕ್ಕಾಗಿಲ್ಲ. ಅವಾಗ ನಮಗೇನು ಬೇಕು, ಇನ್ನೊಂದು ಕ್ವಾಂಟಮ್ ನಂಬರ್ ಬೇಕು. ಅದು ಯಾವುದು? ಸ್ಪಿನ್ ಕ್ವಾಂಟಮ್ ನಂಬರ್. the fourth quantum number is what? A spin quantum number. Spin quantum number. It is designated by M.S. M subscript S. Azimuthal, the magnetic quantum number is M.L. It's a M.S. So here the each orbit can accommodate 2 electrons, means how they are different. Each orbit can accommodate a maximum 2 electrons. How they are different? So you know the revolving of your earth around the sun. During revolving, it revolves its own axis also. ಭೂಮಿ ಸೂರ್ಯನ ಸುತ್ತುವಾಗ ಏನು ಮಾಡ್ತದೆ, ಅದರ ಕಕ್ಷೆಯಲ್ಲಿ ಅದು ರೊಟೇಟ್ ಆಗುತ್ತೆ. ಹಾಗೆ ದಿಸ್ electrons, each electron revolve its own axis. So that means there is a two type of orientation you can find. One is the like this. The electron can rotate in a or revolve its own axis with a clockwise or anti-clockwise direction. That means the two quantum numbers here, the not the quantum number, the type of spin state. The electron has a 2 spin states. That is one is a plus half, another is a minus half. That is, the spin quantum number has a 2 values. Only 2 values is sufficient because you are describing or distinguishing the 2 electron in the orbit. So it has how many values? Plus half and a minus half. So what it describes? The spin states of the electron. Suppose if you write the plus half, means it is spinning a clockwise direction. So it is represented by a minus sign. It is a anti-clockwise direction. So this is the spin quantum number. Spin states of it describes a spin state of the electron, in which direction it's rotates. It's to the own axis. So these 4 quantum number. Now the 4 quantum number characterize or distinguish all the atomic orbital around the nucleus. I think it's clear. So definitely in exam you can find the one question from here. See, one question may be describe the what are the significance of 4 quantum number. The first significance of the principal quantum number is what? It describes the size and energy of the orbitals, and azimuthal quantum number describes the shape of the orbital, and magnetic quantum number orientation of the atomic orbital. The spin quantum number orientation of the electron spin, which direction the electron spin. It's a clockwise or anti-clockwise. Therefore it has only 2 values. So here now next is the shape of the atomic orbitals. So the quantum after the quantum number, next is the shape of the atomic orbitals. Here already we discussed, this is a psi is a wave function. It has no mathematical, it's a mathematical function. It has no physical meaning. It's a function of that type of number. Suppose if x is a function of the square root of 1, means it has either plus 1 or minus 1 its values, because plus 1 into plus 1 equal to 1, minus 1 into minus 1 is 1. It's the real number. Suppose the y is a function of a minus 1, it is not a real number. What are its function? So it is like that. This psi is also, it's a mathematical function. It has no physical meaning. If you, what is is a physical meaning of square root of minus 1? What is your answer? So you cannot, is it a 1 plus 1? No. It is a minus 1? No. say that type of function your size. ಅರ್ಥ ಏನು? psi ಅಂದ್ರೇನು? ಇಟ್ಸ್ ಎ ಫಂಕ್ಷನ್ ಆಫ್ ನಾಟ್ ಎ ರಿಯಲ್ ನಂಬರ್. ಅದಕ್ಕೆ ಅರ್ಥ ಇಲ್ಲ, ಅದಕ್ಕೆ ಫಿಸಿಕಲ್ ಮೀನಿಂಗ್ ಇಲ್ಲ ಅಂತ ಹೇಳ್ತಾರೆ. ಓಕೆ, ಆಫ್ಟರ್ ದ್ಯಾಟ್ ಇಷ್ಟು ಆಯ್ತು ಅಂತ ಹೇಳಿದ್ರೆ ನೆಕ್ಸ್ಟ್ ಬಟ್ ದ ಸಪೋಸ್ ಯು ಡ್ರಾ ದ psi ವರ್ಸಸ್ r for at various atomic orbitals, you will get different plots. Even though it is a no physical meaning, if you draw the psi versus r for that 1s orbital is different from a 2s orbital or 3s orbital, like that. Okay. Now, next is if psi has a no meaning, but the Max Born he has shown that this mode of psi square gives the a probability density of the electron. Probability ಎಷ್ಟು ಪರ್ಸೆಂಟೇಜ್ ನಾ ಇಲೆಕ್ಟ್ರಾನ್ ಅನ್ನು ಕಾಣಬಹುದು ಈ ಪಾಯಿಂಟ್ನಲ್ಲಿ. ದಿಸ್ ಇಸ್ ಕಾಲ್ಡ್ ಎ probability density. So the suppose you draw the a graph of 1s orbital. So this is a what? Rn. It is a nucleus. It is the distance from nucleus, or in picometer you can say, r in picometer. This is the for s orbital, a psi square, mode of psi square is a function of r. For s orbital, the psi square is only varies with the r. What is that meaning? I will later tell. So what is the graph? What is the graph? The graph is like this. ಈ ರೀತಿ ಗ್ರಾಫ್ ಬರ್ತದೆ. So what is the graph shows? The electron density. What is this? Gives the electron density near the nucleus is very high. ಹೌದಲ್ವಾ? ನ್ಯೂಕ್ಲಿಯಸ್ ಹತ್ತಿರ ಬಂದಾವಾಗ electron density ಏನಿದೆ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. If you move away, the electron density goes on decreases. It is not up reaches to 0. You can find some electron density. So this is a curve for 1s orbital. So here what does that mean? Suppose it is a nucleus. Suppose it is a nucleus. This is a nucleus. Where you can find the electron density is more, the maximum electron density you can find the near the nucleus is like this. It's a nucleus. After that the electron density goes on diminishing. See, like this. So it is not ends, it is like this. This is the 1s orbital. Where its maximum, it's near the nucleus. You have the more electron density. If you move away from the nucleus, electron density goes on decreases, and it is not tends to 0. You can find some electron density. You move to the distance of infinity also. So now one thing is here. The psi square is the function of r. What does that mean? If you move from here the distance r, from distance r, the electron density in this point is same. It means the probability of finding the electron in s orbital is only function of r. That means if you move in all direction at the distance r, you have the same electron density. It means the s orbitals are spherical in shape. ನೀವು ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ ಅನ್ನು ತಗೊಂಡ್ರೆ ಈ ಡಿಸ್ಟೆನ್ಸ್ ಎಲ್ಲ ಡಿಸ್ಟೆನ್ಸ್ r ಹೋದಂದರೆ ನಿಮಗೆ ಈ ಪಾಯಿಂಟ್ನಲ್ಲಿ ಏನು ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಸಿಗ್ತದೆಯೋ ಎಲ್ಲ ಡೈರೆಕ್ಷನ್ನಲ್ಲೂ ಒಂದೇ ಇದೆ. ಇದರ ಅರ್ಥ ಏನು? ಇಟ್ ಹ್ಯಾಸ್ ಎ ಸ್ಪೆರಿಕಲ್ ಇನ್ ಶೇಪ್. ದೆನ್ ಫಾರ್ ದ 2s orbital, suppose you draw the 2s orbital, this curve 2s orbital ನೀವು ಬರೆದರೆ it is a psi square, mode of psi square is a function of r, and it's a r in picometer. So 2s orbitals, like this, it touches to 0 like this. See, look at the curve. Here also for 2s orbitals also, your diagram, see at the near the nucleus, you have a very high density of the electron like this. After moving away, you have the electron densities goes on decreases like this. See, like this decreases. At one point, this point, the electron density is 0 on the above this surface, you have an electron density 0. After that, again it has some electron density like this. So this is the probability density of electron at 2s orbital. So this point, the electron density is 0 is called a nodal surface. Node. This surface is called a nodal surface. Above this surface, the electron density is called 0 is called a nodal surface, or it simply is called a node. What is a node? Here the point, here the probability of the finding the electron is 0 is called a node or a nodal surface. For 2s orbital, you have one nodal surface. For 1s orbitals, there is no nodal surface. The electron density is decreases when you move away from the nucleus. See, there is no node in the 1s orbital. What is a node? Here a probability of finding the electron is 0. ನಮಗೆ ಇಲ್ಲಿ ಏನು ಕಾಣಿಸ್ತು, 1s ಆರ್ಬಿಟಲ್ಗೆ ಯಾವುದೇ ನೋಡಲ್ ಪ್ಲೇನ್ ಇಲ್ಲ, ಗ್ರಾಫ್ ನೋಡಿ ಕಾಣಿಸ್ತು. For 2s orbital, we have a node. This point is called a node. After that, boundary surface diagram. One more word is given in a boundary surface diagram. Boundary surface diagram. See, what is that boundary surface? So, what is the boundary for this orbit? So, this is the boundary, or this is the boundary. See, this I can write the boundary surface. There are many boundary surface diagram for this s orbitals. So, suppose I write like this also, it's a boundary surface, because the electron density is not ends. It is some electron density you can find at infinite distance from the nucleus. ಎಷ್ಟು ದೂರ ಹೋಯ್ತಂದ್ರೂ ಸ್ವಲ್ಪನಾದರೂ ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಇರುತ್ತೆ. ಬೌಂಡ್ರಿ ಸರ್ಫೇಸ್ ಅಂದರೆ ಏನು ನಮ್ಗೆ ಹಾಗಾದರೆ ನೋಡಿ, ನಾನು ಇಷ್ಟೇ ಚಿಕ್ಕದು ಸರ್ಕಲ್ ಮಾಡಿದರೆ ದಟ್ ಈಸ್ ಆಲ್ಸೋ ಬೌಂಡ್ರಿ ಸರ್ಫೇಸ್, ಬಟ್ ದೇರ್ ದ ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ ಆಫ್ ಫೈಂಡಿಂಗ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ ಈಸ್ ಅಬೌಟ್ 60% ಇರ್ಬೋದು. ನಾವು ಇನ್ನೂ ಸ್ವಲ್ಪ ದೊಡ್ಡ ಸರ್ಕಲ್ ಮಾಡಿದರೆ ದ ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ ಆಫ್ ಫೈಂಡಿಂಗ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ ಒಂದು 70-80 ಇರ್ಬೋದು. ಬಟ್ ಬೌಂಡ್ರಿ ಸರ್ಫೇಸ್ ಡಯಾಗ್ರಾಮ್ ಏನು ಹೇಳುತ್ತೆ ಅಂದರೆ ದ ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ ಆಫ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ ಈಸ್ ಅಬೌಟ್ 90%. ಸೊ ದಿಸ್ ಇಸ್ ದ ಸರ್ಕಲ್, ದಿಸ್ ಇಸ್ ಕಾಲ್ಡ್ ಎ ಬೌಂಡ್ರಿ ಸರ್ಫೇಸ್. ಈ ಬೌಂಡ್ರಿಯನ್ನು ಹಾಕಿದ್ರೆ ಅಂದರೆ ನೀವೇನಿರಬೇಕು, ಆದರೆ ಆ ಬೌಂಡ್ರಿ ಒಳಗೆ ನಿಮಗೆ 90% ಎಲೆಕ್ಟ್ರಾನನ್ನು ಕಾಣುವ ಸಾಧ್ಯತೆ ಇರಬೇಕು. 100% ಯಾಕಿಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ಆಲ್ರೆಡಿ ಹೇಳಿದ್ದೀನಿ, ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಇದು ಇಟ್ ಇಸ್ ನಾಟ್ ಟೆನ್ಸ್ ಟು 0. ಇಲ್ಲೇ ಬಂದು ಮುಟ್ಟಿದ್ದು 0 ಆಯಿತು ಅಂತ ಹೇಳಿದರೆ ನಾನು ಈ ಡಿಸ್ಟೆನ್ಸನ್ನು ಬೌಂಡ್ರಿ ಅಂತ ತಗೊಳ್ಬೋದು. ಇದನ್ನು ರೇಡಿಯಸ್ ಆಫ್ ದ ಬೌಂಡ್ರಿ ಅಂತ ತಗೊಳ್ಬೋದಾಗಿತ್ತು, ರೇಡಿಯಸ್ ಆಫ್ ದ ಸ್ಪಿಯರ್. ಬಟ್ ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಈಸ್ ನಾಟ್ ಎಂಡ್ಸ್ ಟು 0. ಒಂದು ಪಾಯಿಂಟಿಗೆ ಬಂದು 0 ಆಗೋದಿಲ್ಲ. ಇಟ್ ಸ್ಲೋಲಿ ಇಟ್ ಇಸ್ ಎ ಸಮ್ ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಯು ಮೂವ್ ಅಟ್ ದ ಇನ್ಫೈನೈಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಆಲ್ಸೋ. ಅದಕ್ಕೆ ನಾವೆಂತ ಹೇಳಿದರೆ ಒಂದು ಬೌಂಡ್ರಿಯನ್ನು ಹಾಕ್ತೀವಿ, ಆ ಬೌಂಡ್ರಿ ಒಳಗೆ ಎಷ್ಟು ಬರಬೇಕು, ನಮಗೆ 90% ಎಲೆಕ್ಟ್ರಾನನ್ನು ಕಾಣುವ ಸಾಧ್ಯತೆ ಇರಬೇಕು. ದಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಎ ಬೌಂಡ್ರಿ ಸರ್ಫೇಸ್ ಡಯಾಗ್ರಾಮ್. ಸೊ ವಾಟ್ ಈಸ್ ದ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ 1s and 2s? The size of the 1s, the size, suppose 1s and this is a 2s. The size wise they are different. One more is the 2s orbital, you have a one nodal plane or node. say node is where the area where the probability of finding the electron is 0. For the 2s, for the 3s, if suppose you draw the graph for 3s, you will graph say like that 1, 2, like this. Like this. So you can find the two nodal pair. For the 3s orbital, you can find the two nodal pair where the probability of finding the electron is 0. This is called a node. This is also called a radial nodes. How many radial nodes are there for s orbitals? S orbitals ಗೆ ಎಷ್ಟು radial nodes ಇದೆ ಕೇಳಿದ್ರೆ ಏನಂತೀರಿ? The actually for any orbital, the number of radial nodes for any orbital n minus l minus 1, n minus l minus 1. For s orbital, well, you know what is the value of l. For s orbital, l is equal to 0, therefore it becomes n minus 1. How many radial nodes are there for the s orbital? n minus 1. ರೇಡಿಯಲ್ ನೋಡ್ ಅಂದ್ರೆ ಏನು? ಆ ಒಂದು ಜಾಗದಲ್ಲಿ ನಮಗೆ ಎಲೆಕ್ಟ್ರಾನನ್ನು ಸಿಗುವ ಸಾಧ್ಯತೆ 0 ಇರ್ತದೆ. ಅದಕ್ಕೆ ನಾವೇನಂತೀವಿ ನೋಡ್ಸ್ ಅಂತೀವಿ. ಸಿ ಎಸ್ ಆರ್ಬಿಟಲಿಗೆ ಇದಕ್ಕೇನಂತೀವಿ ರೇಡಿಯಲ್ ನೋಡ್ಸ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಎಷ್ಟು ರೇಡಿಯಲ್ ನೋಡ್? ಫಾರ್ ಎನಿ ಆರ್ಬಿಟಲ್, ಪಿ ಆರ್ಬಿಟಲ್, ಡಿ ಆರ್ಬಿಟಲ್ ಆರ್ ಎನಿ ಆರ್ಬಿಟಲ್, ಹೌ ಮೆನಿ ರೇಡಿಯಲ್ ನೋಡ್ಸ್ ಆರ್ ದೇರ್? ಎನ್ ಮೈನಸ್ ಎಲ್ ಮೈನಸ್ 1. ಫಾರ್ ಎಸ್ ಆರ್ಬಿಟಲ್ ಯು ನೋ ಇಟ್ಸ್ ಎ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಎಲ್ is equal to 0. Therefore, how many nodes are present? n minus 1 nodes are present. For example, suppose you take the 1s orbital. 1s orbital ಈ ನಂಬರ್ ಏನು ಬರೀತೀರಿ ಅದೇನದು a principal quantum number n. Therefore, 1 minus 1 equal to 0. So, s orbitals there is no nodes 0. For 2s orbitals, 2 minus 1 is equal to 1. So we can find the one node for your 2s orbital. This is a one node. For 3s orbitals, 3 minus 1 equal to 2 nodes. Like that, you can find out the number of nodes for each s orbital. Clear? See, ಏನಿದು probability density. ಹೇಗೆ probability ಡೆನ್ಸಿಟಿಯನ್ನು ಮಾಡ್ತೀರಿ? ಎಸ್ ಆರ್ಬಿಟಲ್ಸಿಗೆ ನೀವು probability ಡೆನ್ಸಿಟಿಯನ್ನು ಹೇಗೆ ಕಂಡುಹಿಡಿತೀರಿ? ದ psi square is a function of r versus the what is the horizontal axis? X axis is what? The distance from the nucleus. So on this basis you can find out the shape of the orbital. Shape of the orbital ಅಂದ್ರೆ ಏನು? The maximum 90% probability of finding the electron. Area 90% probability of finding the electron. ನಮಗೆ ಎಸ್ ಆರ್ಬಿಟಲಲ್ಲಿ ಏನೇನು ಕಾಣಿಸ್ತದೆ? ಒಂದು, ಈ ಸೈ ಸ್ಕ್ವೇರ್ ಇಸ್ ಎ ಓನ್ಲಿ ಫಂಕ್ಷನ್ ಆಫ್ ಆರ್. ನೀವು ಡಿಸ್ಟೆನ್ಸನ್ನು ಎಲ್ಲ ಕಡೆ ಯಾವುದೇ ಡಿಸ್ಟೆನ್ಸಿಗೆ ಹೋಗಿ ಅದು ಯಾವುದೇ ಎಲೆಕ್ಟ್ರಾನ್ ಪ್ರೊಬ್ಯಾಬಿಲಿಟಿ ಈ ಸೇಮ್ ಇನ್ ಆಲ್ ದ ಡೈರೆಕ್ಷನ್. ದೆರ್ಫೋರ್ ಇಟ್ ಇಸ್ ಎ ಸ್ಪೆರಿಕಲ್ ಶೇಪ್ ಅಂತಿದೆ. ದಿಸ್ ಇಸ್ ದ ಸಿಂಪ್ಲೆಸ್ಟ್ ಶೇಪ್. ದ ಆರ್ಬಿಟಲ್ ಆಫ್ ದ ಸಿಂಪ್ಲೆಸ್ಟ್ ಶೇಪ್ ಈಸ್ ಎಸ್ ಆರ್ಬಿಟಲ್. ಸೊ ಸಿಮಿಲರ್ಲಿ ಆಫ್ಟರ್ ದಟ್, the shape of the p orbitals. For p orbital, L is equal to 1, M is equal to minus 1, 0, plus 1. L is equal to 1 ಅಂದರೆ p orbital, M is equal to minus 1, 0, plus 1 ಅಂದರೆ it has a 3 orientation. 3 ಕಡೆ 3 ಡೈರೆಕ್ಷನಲ್ಲಿ ಓರಿಯಂಟೇಷನ್ ಆಗ್ತದೆ. Therefore, what are the direction? One is taken as a, this is a x axis, it's a z axis, it's a y-axis. So these three, how they are oriented? One is oriented along the x-axis, and one is oriented along the y-axis, and another is a z-axis. Here also the probability density gives the what it gives the two lobes. one lobe here, or you can write another lobe here. So this is the shape, the two lobes, it is a meets at the nucleus. Here at the meeting point you have a 0 probability of finding the electron. So this is the shape. This is called, if it is oriented along the x-axis, then it's called a px orbitals. Px. See what is the shape of the p orbital? It has a 2 lobes. It meets at the center of the nucleus. So similarly, if you want, if the 2 more are what? This is a like this actually. It's a y-axis, x is a z. Y, z, it's x. So all are same shape. I have the size wise I have written little bit differently. So this, but how they are differ? If the orbitals having a same L means they have the same shape, because L defines the shape. L defines the shape. This is a px, py and pz. They have the 2 lobes. Each orbitals have the 2 lobes. So here how they are differ? They are differ by the orientation. One is oriented as along x-axis. It's called px, py and pz. Okay. What about the node plane? Suppose you take a px orbital. So here along the xy plane, you cannot find any electron density here. Along the it's x orbital, yz plane. For this is oriented along the x-axis, means you don't have a electron density at the yz plane. This is called angular nodes. In s orbital, I discussed the radial nodes. So suppose you take the px orbital, you have no electron density on this xy plane, yz plane. This is called angular node. The other in s orbital we have discussed the radial node. So here how many angular node? For each orbital there is one angular node. So suppose you take it's a pz, you don't have a electron density at xy plane. Here if you take the py, then you don't have a electron density in the your xz plane. These are called angular node. How many angular nodes are present? For any, the number of angular nodes is equal to L. L means for s orbital L is equal to 0, that means there is no angular nodes. For p orbital L is equal to 1, it's a one angular node. So what about the radial nodes? So 1s orbital you have taken, it's a radial node equal to 0. Similarly, first 2p orbital, p orbital is what? 2p orbital. Idikke radial node is to 0, but it has a one angular node. So angular node equal to L, radial node is equal to what? N minus L minus 1. So here for 2p orbitals, N is equal to 2. For p orbital, L is equal to 1, minus 1 equal to 0. Suppose you take the 3p orbitals, then you have a one radial node. See, radial nodes where you can find, this is the first orbital, is ends. Then you have some electron density, here you can find the 0. After that, one more orbital, like this. This is called a radial nodes. This is called a radial nodes for the p orbital. So See, s orbital, how do you show? Electron density ends, and again you have a small area, you don't have a electron density, and after that electron density again starts, the probability of electron density. Here also for p orbitals also, the electron density of like this, after that you some area you have don't have a electron density, after that again the electron density start. This is called, this area is called, what this area is called? Radial nodes. The 2p orbitals has no radial nodes because this is the first p orbital. 3p has a 1 radial nodes. So similar, how many radial nodes are there? n minus l minus 1. 2p means how many radial nodes? n is equal to 2, l is equal to 1 for p orbital, l is equal to 1, minus 1 equal to 0. For 3p orbital, 3 minus 1 minus 1 is equal to 1. 3 minus L minus 1. So, this is the shape of the p orbital. At least, it has a 2 lobes. P orbital has a 2 lobes. It looks like a dumbbell. Dumbbell, a dumbbell, it's called as a dumbbell shape also. It has a 2 lobes. So, it's a the either side of the nucleus. On the 2 lobes are either side of the nucleus. There are the 3p orbitals. ಯಾವ ರೀತಿ ವ್ಯತ್ಯಾಸ ಆಗಿರ್ತದೆ, ಓರಿಯೆಂಟೇಷನ್ ನಲ್ಲಿ ವ್ಯತ್ಯಾಸ ಆಗಿರುತ್ತೆ. ಒಂದು ಎಕ್ಸ್ ಆಕ್ಸಸ್ ಕಡೆ, ಇನ್ನೊಂದು ವೈ ಆಕ್ಸಸ್ ಕಡೆ, ಇನ್ನೊಂದು ಝೆಡ್ ಆಕ್ಸಸ್ ಕಡೆ ಓರಿಯೆಂಟೇಷನ್ ಇರುತ್ತೆ. ಸೊ ಆಫ್ಟರ್ ದಟ್ ದ ಒನ್ ಮೋರ್ ಈಸ್ ದ d orbitals, the shape of the d orbital. So the shape of the d orbital we can discuss in a next class. Anyway, thank you.